Hello and welcome to Stat 441. This is in this video lecture. I will present a simple linear regression example. The data set and the R code used is you can find it along with the PowerPoint lecture in Blackboard. So you can use that to run your code and then look at the output yourself. Okay, so this will show you all the steps. Again, the same example is also posted as the homework assignment for this week. So you can use the questions as reference and how to write the answers for completing the regression analysis. Okay, so we will assemble what we have seen so far, all the elements that are used to fit and use a straight line regression model. And this time we will use a computer program to perform all the calculations. Okay, here's an example. Suppose a fire insurance company wants to relate the amount of fire damage in major residential fires to the distance between the residence and the nearest fire station. The study is to be conducted in a large suburb of a major city. A sample of 15 recent fires in this suburb is selected. The amount of damage y and the distance x between the fire and the nearest fire station are recorded for each fire. Okay, so this is our data set. This is our x variable, the independent variable, which is distance from the fire station in miles. Okay, so 15 observations. And for each distance, we have a dependent variable, which is the fire damage in thousands of dollars. So for distance 3.5, the damage was to 26.2. For 4.6, it's 31.3, and so on and so forth. So this is the data that is collected. Okay, now the first step is to just make a simple scatter plot of your variable x versus y to see if the linear model is appropriate. Now here we have our data points. As you can see, they are forming a pretty straight line here. So we will try to fit a straight line model to this and then use that for prediction. Okay, so here are the steps. The first step is that we will have a model that we want to fit. So in this case, we want to fit a straight line model of the form y equals beta 0 plus beta 1 x. So this is the equation of a straight line. We want to fit that model. The next step would be to enter the data into a computer and then use a statistical software to run the regression analysis. So the R code is available, and I'll show you how this looks in SAS just in comparison, and then how the R output for simple linear regression looks like. So this is what the SAS output looks like. Here are your parameter estimates, the test statistic values, the p-value, the confidence interval, and then here is the R squared value. And then for R, this is what it looks like. Here is the estimate of beta 0 and beta 1, the test statistic, the p-value. Here is the R squared, the multiple R squared that we will use to figure out the strength of the model. So let's use this information. Okay, so here are the estimates for beta 0 and beta 1. Beta 0 is 10.2779, beta 1 is 4.9193. Okay, now this is the least square model. Y hat is equal 10.278 plus 4.919 times x, which is a straight line equation. Y equals mx plus b form. Here we are calling it beta 0, the intercept, and beta 1 is the slope. Now the interpretation in terms of the problem for these two numbers. So let's look at the slope first, 4.919. So what that means is that for each 1 unit increase in the distance, for each 1 mile increase in the distance, the estimated mean damage increases by $4,920. Okay, it's rounded to 4920 here. The y-intercept will be that if the fire is 0 miles from the fire station, it has an estimated mean damage of $10,280. Well, in this case, it's not logical, but that's the interpretation of the y-intercept. The next step will be to check the assumptions, and here is a list of the 4 assumptions. First is the error terms. The mean of the errors are 0. The variance is constant. Errors are normally distributed, and errors are independent of each other. Okay, so this is what the residual plot for SAS looks like. So these two pretty similar. This one is the X versus the residuals. This is the fitted values versus the residual, but both are giving the same result. Basically for 1 and 2, the first and the second assumption, we are looking for no pattern. So here we don't see any specific pattern. That means the first 2 assumptions are good. This is for the third assumption, which is normal residuals. Again, all the points are close to a straight line. In R, we will use the first plot and the second plot. So first plot for assumptions 1 and 2, you're not seeing any specific pattern here. So the linear model is appropriate. The mean is 0 for the residuals, or the mean error is 0, and the variance is constant. Here again, the points are close to a straight line on the normal QQ plot. That means the residuals are normally distributed. Okay, so here's the summary of the residual analysis. So the residual plot shows no trends are detected on either graph. So first and second assumptions are satisfied. Mean error is 0, constant error variance. The QQ plot, the points fall in a straight line. So the assumption of normal errors is also satisfied. And the fourth assumption is that we have independent errors. So which is again, since the way the data was collected, each of the fires were independent of each other. So that way the residuals are also independent of each other. Here is the next step. We will test the model utility. Basically, we will test to see if the beta 1 term is significant. So we can conduct a two-sided or a one-sided test. H0 beta 1 equal to 0 versus HA beta 1 is greater than 0. So we're testing for a positive slope in this case. We could test for a not equal 0, which will also give us the conclusion that beta 1 is significant. Okay, now the computer output for the test statistic is 12.525, and the p-value is always two-sided on the computer output. So if you need a one-tail test, then you have to divide the p-value on the output by 2. So on the output, it's 0.0001. We divide it by 2, so it's a very small p-value. We will reject the null hypothesis. That means beta 1 is significant. What that means is that there is sufficient evidence to reject H0 and conclude that the distance between the fire and the fire station contributes to the information about the prediction of fire damage. So basically, a linear model is appropriate in this case. Okay, then we can create a confidence interval for the slope R. We can do that using R. So this is what we will use. The command confint, and then this is where the regression is saved, and then we can choose the level. Again, for details, watch the R videos. Okay, we can create a 95% interval here for beta 1, so which basically says or the interval indicates that we are 95% confident that between 4070 and 5768 will be the mean increase in damage per additional mile distance from the fire station. Okay, then we can find the R squared value from the output. Again, in this case, R squared is 0.9235, which indicates that approximately 92% of the sample variation in the fire damage is explained by the distance x between the fire and the fire station, which is a pretty high value, 92.35%. If you look at the correlation coefficient, R, it's the square root of this number. Square root of 0.9235 is 0.96. So again, a pretty high value of the correlation coefficient. So X and Y have a strong linear relation. That's what this value indicates. Okay, so now if we look at what we have so far, we have a significant beta 1 value. We have a high value of R squared. We have all the assumptions are met. So we have a pretty strong linear relation between X and Y. Okay, so based on this, we can use this model to now predict the fire damage based on the distance from the fire station. So let's say there is a residential fire at 3.5 miles. What would be the predicted fire damage that the insurance company can use? So plug in 3.5. Again, this you can find this code attached along with the PowerPoint lectures and also in the video. So if you choose distance at 3.5, then the point estimate is 27.49. Okay, so 2,749 versus this is our prediction interval, and this is the confidence interval for the damage. Here is the summary. So Y hat, the point estimate is 27.49. The prediction interval is from 22.3239 to 32.6672. So basically, in words, we can predict with 95% confidence that the fire damage for a major residential fire 3.5 miles from the nearest station, this was in thousands of dollars, so 22,324 to 32,667. Okay, now one last thing, when you're using a model like this, you have to be aware that this model can be used for prediction for the values of X that we have observed, so within that range. So the original data range from 0.7 to 6.1 miles. So approximately this range is what this model can predict. We cannot use this for way outside the range. So for example, we should not use this model to, let's say, predict the damage if a fire occurs 20 miles away. Okay, because we have not observed anything in that range. So you have to kind of stick within this, let's say between like 0.5 and let's say up to 7 miles. But if we start to go beyond that, that will be just extrapolation. Right, so this is the complete example. Please check the homework assignment for this week. Also check the PowerPoint lecture, which has the code and the data set for this example. All right, thanks for watching.